right, let's do chapter 10, which is on, whoopsie, undo, prime numbers. Now, the Greeks investigated numbers significantly because they wanted to understand their world and the universe and everything they saw. And they realized that some numbers, and we're specifically talking about positive integers, are special. And we are going to call them prime numbers. So first, what is a prime number? A prime number is a positive integer. So we're only looking at positive integers. In elementary school, we would call them whole numbers. A positive integer, first of all, it has to be greater than 1, greater than 1. And so let's say first of all here. And secondly, it has to, the only divisors, let's say here like this, greater than 1, and the only divisors that it has are 1, because 1 divides into everything, and the number itself. Now, for example, 1 is not a prime number because we are looking for numbers greater than 1. And 1 is special, so it doesn't really follow the same rules and therefore can't be included in this definition. 2 is a prime number because the only divisors are 1 and 2 itself. Same for 3. 3 is a prime number. 4 is not a prime number because it is divisible by 2, something in between 4 and itself. And so on and so on. You can make a list. And let's actually make a list of the first prime numbers to just get a look at them. And also what I want to do is as we make this list, which will start with 2, 3, 5, and so on, we'll continue this in a second. As the numbers are getting bigger, try and be aware of your thought process in deciding if it's a prime number. And notice how it's getting more and more difficult to conclude that it is a prime number. So the next one can't be 6 because 6 is divisible by 2 and 3. Next one will be 7. 8 is even. So obviously any even number won't appear in this list after 2 because it'll be divisible by 2. So 8, isn't it? 9 divisible by 3. 10 divisible by 2, among others. You just need to find one that is between 1 and itself. The only divisors can be 1 and itself. So 10 is not going to do it either. 11 does. And 13. Not 14, not 15, 16, but 17. 18, 19, 19, yes. So I want to go slowly here so that you can think about it and think about how easy or difficult is it to determine as I'm going one number at a time whether it's a prime number or not. What is the next prime number? The next one is 23. What about the next one? You can go 24, 25, 26, 27, 28, and eventually you'll get to 29. And the next one, you don't have to go that far, and you'll get to 31 is indeed a prime number. But it's becoming less and less obvious whether or not the number is prime or not, because the larger the number, the more possible divisors I need to check before I'm 100% sure that it is a divisor. We'll go up to, let's say, up to 50. Next one is, I have to go all the way up to 37, not 38, not 39, not 40, but 41. Let's do one more. What is the next prime number? It's 43. And then I go to 47. And I can keep going. And the further I go, the larger the number, the more difficult it is to decide whether or not a number is prime. And in fact, to determine if a number is a prime number or not is a really hard problem. Now, our numbers aren't that big, but we can keep going, bigger and bigger numbers, and it's really difficult to decide with 100% certainty whether or not that number is prime. So one thing we can ask next is, how can we decide what is a first step to decide if a number is prime or not? How can we start to find more prime numbers as a first step? Well, for that we're going to go to 10.2, and the Greeks did of course ask this question and also answered it in a basic way as a first step around 300 BC. And a person by the name of Eratosthenes came up with a sieve where you'd start with all the numbers and decide if they're prime or not until you've sifted out all the prime numbers. So let's have a look at that next. Let's have a look at what he did. So if we look at, let's say, the first 400 numbers, and we want to figure out which ones are prime, which ones are not. The ones that are not prime should obviously go, and I want to be left with just the prime numbers. Well, first of all, let's pick the first prime number. That is a 2. When I select the 2, all other multiples of 2 should go away because they cannot be prime numbers. 2 divides into them. So look what happens when I click on the 2. All the other multiples of 2 are selected and removed. They cannot be prime numbers. The next number in line, we're not looking at the 1 because we know 1 is special and not a prime number. The next number in line after 2 is 3. 3 is the next prime number. And once I select 3, all multiples of 3 have to go away. So I select 3 and then see all the multiples of 3 that have not been taken away are taken away. Let's do that again so that you can see what happens, because it may have been a little fast. So I select the first prime number, which is 2. And then the next number in line is a prime number, which is 3, which we already know. Select it, and then all the multiples of 3 not removed yet are removed. Now I know 4 is not a prime number because it was removed when 2 was selected. The next number in line is a 5. That is the next prime number. Selecting it will remove all the multiples of 5 that have not been removed yet. So for example, 25 will be removed, whereas the next one, 35, will be removed, and so on. So keep an eye on them as I select 5. All those have to go. They're divisible by 5. The next number in line is a 7. Now let's think about this. All multiples of 7 that have not been removed yet should be removed. What about 14? It is the next multiple of 7, but it's already gone. Why is it already gone? Because when I consider 2, 2 divided into 14, because 2 times 7 is 14. So 14 was removed when I eliminated all the multiples of 2. So by the time I get to 7, 14 is already not there. What about 21? 21 is gone. Why? Because it's 3 times 7. And when I considered 3, 21 was removed. So then what is the first multiple of 7 that is not removed? It can't be 2 times 7, 3 times 7, 4 times 7, 5 times 7, 6 times 7, but it will be 7 times 7. So where is 49? And you see there, 49 is right there. It's not removed yet. And when I click on 7, 49 should be removed, as well as other multiples of 7 that are coming up past that. 49, and there are actually quite a few. Now we continue to 11. What is the first multiple of 11 that is still remaining in my list, that is not removed yet? It can't be 2 times 11 because it would have been removed when I looked at 2. 3 times 11? When was 4 times 11 removed? When I looked at 2. 5 times 11 is gone, and so all the multiples of 11 are gone except the first one is 11 times 11. It's not removed yet, and it's sitting right over there, 121. It should be gone, and when I click on 11, it will go with any other multiple of 11 that comes after it. And you see there are still a few there. So now the question becomes, how far am I going to go on this list? Because of this property of the sifting method, that when I look at a number, a prime number, a new one in the list, many of its multiples are already gone. It means that I'm not going to need to check every single number. But after a while, the next multiple isn't going to be there, and I can stop. When I look at 13, do I need to look at 13? Is there anything that will be crossed out, that should be removed, that isn't removed yet? 13 times 13 is the first one, or 13 squared, which is 169. And it's still there, so I need to look at 13. Click it, and a few of them still need to be removed. 17? What is the first prime number that, sorry, not the first prime number. What is the first multiple of 17 that has not been removed? 17 times 17. Now the question is, I need to check 17 if 17 times 17 is still under 400, meaning still on my list. And it's 289 and it's sitting right there. So I do need to check 17. Keep an eye on 289 as I click 17 and it goes. And there happen to be some more. Now I look at 19 as the next prime number. Should I even check 19? Well, the first possible number that's not prime that will get removed by checking 19 is 19 times 19, which is 361, which does fall under 400. So I probably should check and keep an eye on 361 as I click 19. There it goes, and it was the only one. And because the next number in line is 23, 23 squared, 23 times 23 is possibly the first non-prime number that would get eliminated. But that's past my 400 list. And if I'm interested in only finding the prime numbers up to 400, I don't need to check 23. Any multiple of 23 will already have been eliminated when I looked at the earlier prime numbers. And I'm left with all the prime numbers all the way up to 400. Even though I only checked up to 19, I get all the prime numbers up to 400. So that's quite a good return. I don't have to check everything, just up to a point. Well, now what is that point? Is the question. Well, let's go back and write some stuff down. So let's say it like this, to find all prime numbers up to, in our example, 400, we needed to check 2, 3, 5, 7, all the way up to 19. 19 squared was 361. Now, the next number in line was 23 squared. And because that is 529, you see here, 529, it's bigger than 400, so we won't need to check it. So let's go back here and write that down. So the next prime number in my list was 23, but 23 squared, in other words 529, was the first one that would need to be eliminated, but it's past 400. So this is less than 400, and this is greater than 400. And if I'm looking to find all prime numbers up to 400, I don't need to check these. Nothing new will be eliminated. I only need to check up to 19. So in general, if I want to, let's say it here, if we want to test, we want to find all prime numbers up to a point or test a number, let's call it n. What do we need to do? We simply need to check the divisibility by 2, 3, 5, 7, and I keep going up to some prime number p. How do I decide what p is? Well, how did I decide 19? The square of that prime number should be less than the number in question, 400 or any number n. So let's say here, with P the largest prime number such that P squared is still under, well, it could maybe equal it, my number N. So give it some thought. It's not as bad as it may seem once I look at something a little more practical. In the case of 400, I stopped because the prime number after 19, that number squared was too big. 19 was the largest, but it depends on the number. I go until the prime number in question, its square is too big. Its square is too big. So let's look at some exercises. And let's look at exercise 10.1 in the book. It says to determine if the following numbers are prime numbers. First up, 682. 682. Sorry, that's an ugly 8. 82. Is that a prime number? Not prime. But you also have to be able to give a reason. In this case, it's an even number. It's not 2. So the reason is it's divisible by 2. Remember, if it's not prime, it has a divisor between 1 and itself. The next number is 71. Oops, why do I keep doing that? There we go. 71. Is that a prime number or not? Now remember, you can't guess, oh, it looks prime. Sometimes a number that looks prime is in fact not prime. It's just so big I can't find that divisor. It may have so few divisors. So I'm not sure. Let's test it. We'll check divisibility by 2. No, 2 doesn't go into that. It's odd. 3. It's not divisible by 3 because the sum of the digits is 8. So my divisibility tests make it a little bit faster to do these small checks. I don't have divisibility tests for everything, but for some. 5, no, it doesn't end in a 0 or a 5. 7, do I need to check 7? Yes, because 7 squared, can do a better arrow than that. 7 squared is 49. 49 is less, so I need to check 7. Now 7 doesn't have a convenient divisibility test, but the number's small enough that I can just divide into 7. Clearly 7 doesn't go into it. Next prime number is 11, but 11 squared is 121, which is bigger than the number in question. So I don't need to test. No need to even consider them. And because the divisibility failed in those numbers, those prime numbers that I should check, I can conclude with confidence now that it is a prime number. So we need to know how far to go. And sometimes I might have a divisibility test, sometimes I don't. The next one is really big, 787845. 787845. Now, of course, if I have a number this big, my list is going to be ridiculous. Ridiculous. Why do I keep drawing these lines? Let's try and get rid of that. Clean things up here. So there has to be it has to fall under one of my divisibility tests. There's no way. If this is prime, it'll be too much work for us to find by hand. So In this case, clearly it's not prime. Sorry, that doesn't even look like an R. There we go. Prime. And the reason is it's divisible by 5. And maybe some others. I just need to find one. So sometimes the number's really big, and obviously it's sort of like a trick question. Last one, 35981. 35981. 35981. It's not huge, but it's not small. So I suspect it's not prime for our purposes of having a question like this, but I would need to have a reason. So can we find a number that is divisible by this guy? Well, not 2. Adding up the digits, that's 8. 8 there, 17, 25, 26. Oh, that is not divisible by 3. That's unfortunate. Looking at the last 2 digits, 4 doesn't divide into that. The last 3-digit number, no, I don't like 8. 5, 6 didn't work because 2 nor 3 didn't work. 7 doesn't have a nice test. I'm already sort of stuck with 11, aren't I? So let's do a little check. Remember, right to left. 1 minus 8 plus 9 minus 5 plus 3. That's not divisible either, because what is this? This is negative 7. Negative 7 plus 9 is 2. Minus 5 is negative 3 plus 3. Oh, it's 0. I was too quick. So that means it is not prime because it is prime? Prime. Because it is divisible by 11. So again, a big number, probably not prime because it'll be too hard for us to check by hand. But you have to find the reason. You have to find the reason. All right, now we have one more sort of little exercise, 10.2, where we are asked, let's just write it down here, where's my cursor? Exercise 10.2, where we're asked to determine if the following statement is true or false. The largest prime number, p, such that p squared is less than or equal to 1,000 is 29. True or false? Well, so let's see, what is 29 squared? What is 29 squared? You get out your calculator. I'll grab mine because I'm not expecting you to know these larger ones by heart. 29 squared is 841. And yes, that is less than 1,000. But is it the largest prime number? Well, what's the prime number after 29? It's 31. And what is 31 squared? I'll give you a chance to calculate it. It is 961. Oops. 961. But that's also less than 1,000. So 29 is not the largest prime number that satisfies this condition. So the statement is false. So things like this feature in the test to see if a larger number is prime, because I have to go as far as I need to go, and I need to know how far I should go in my list of prime numbers. If I stop too early, I might miss it and make the wrong conclusion. If I go too far, well, then I'm just making work for myself. And I don't want to do that either.